Okay, welcome back. Now today we will study about nitric acid. Now last we had seen about the oxides of nitrogen. Now we will see nitric acid. It's also called as aqua fortis. It is written there. Now we will be studying about the lab preparation, about Oswald process. Yes, and then its reaction. Okay, concentrated HNO3 as an oxidizing agent. Okay, O2 added. Then concentrated HNO3 reaction with H2O. Then concentrated HNO3, how it will react and form different products with metals in its dilute form and also in its concentrated form. Then dilute and concentrated HNO3, what is its effect on nonmetals, and finally about the brown ring test. So now we have the lab preparation of HNO3, that is aqua fortis. Lab preparation usually asked as complete the following reaction. Okay, NaNO3, that is sodium nitrate or potassium nitrate, okay, is treated with the H2SO4. H2SO4 can be written as HSO4, H plus and HSO4 minus. Okay, so Na goes with this HSO4, Na and HSO4, see NaHSO4 plus HNO3, this one goes with NO3 minus. So this HNO3 is formed. Along with that, sodium bisulfate is formed. You will know that its name can also be told as, given as sodium hydrogen sulfate. Okay, according to IUPAC, you know that. Now KNO3 also has the same kind of reaction. KNO3 also undergoes the same kind of reaction. If it is potassium nitrate or sodium nitrate given to complete the reaction, it has to proceed. It will proceed like this only. Okay. So we take a potassium nitrate and treat it with, that is, we are treating with a sulfuric acid. We will get potassium bisulfate and HNO3. So this is the lab preparation. It is never asked as lab preparation of HNO3. It is always asked as complete the reaction. Now we will see the preparation of HNO3, the commercial preparation. It is called by the name Ostwald process. Now Ostwald process, it is often defined as HNO3 obtained by catalytic oxidation of NH3 by atmospheric nitrogen. So ammonia we take, and it is and with atmospheric oxidation oxygen, it is oxidized catalytically. That means in the presence of a catalyst, it is oxidized. NH3 is oxidized to NO. Okay, so and from there we are preparing HNO3. So it is obtained by the catalytic oxidation of NH3 by atmospheric oxygen. Now you can see that here ammonia NH3 is reacting with the oxygen, okay, from air in the presence of a catalyst. See what is given here, platinum rhodium gauze catalyst. Okay, what is it? Platinum rhodium gauze catalyst. Now this one is important, and see the temperature is also important, that is 500 K and an iron bar. Okay, and what is formed? NO is formed, NO and H2O. Okay, so that's the first step. Then we take that NO and react again with oxygen to form NO2. So NO2 formed dissolves in water and give HNO3. That is NO2 we will take and dissolve in HOH, that is water only. NO2 and this OH goes together and form HNO3. Understood? And then hydrogen and HNO3, and then NO will come out. I hope you got it. So this is how we are doing the preparation of HNO3. Now this catalyst, I told you, this has to be mentioned. The temperature has to be mentioned. The pressure also has to be mentioned. Otherwise you are not going to get marks. Now PT, that is platinum and rhodium, they are very unreactive, you know that, isn't it? So they are used as gauze catalyst, means in the form of a gauze, in the form of a mesh they are made, and this ammonium is made to, gas is made to be oxidized with that. Okay, and as you know, HNO3 is a very reactive acid, you know that, oxidizing any metal, isn't it? So that kind of a reaction is not possible with the platinum, isn't it? Platinum is a very unreactive metal. So with platinum it is not possible, and as a result platinum is used here. So it's very definitely important to mention that platinum rhodium gauze catalyst is used. And it can be converted and concentrated by, once HNO3 is prepared, it can be concentrated up to 68%, and further concentration to 98% is achieved by dehydration with the concentrated H2SO4. This is also an added information. So this much you should be knowing. So now we have the physical properties of HNO3. You can see it's a colorless liquid. The lab grade is 68% HNO3. Then specific gravity is 1.504. And it is a planar molecule. I mean the structure, it's not very important, but if you should know it. See, two nitrogens are combined together, connected together by a single bond, nitrogen, here oxygen and here hydrogen. Okay, and then the bond length, bond angle, everything is mentioned. Okay, here this one will be the least bond angle. Okay. Now, it is a planar molecule. When it is a strong acid in water, how does it behave as an acid? HNO3, when it is put in water, it forms H3O plus ions and NO3 minus. So, H3O plus ions, hydronium ions are produced in large amounts. So, it is a strong acid. Complete dissociation happens. Then, concentrated HNO3 is a strong oxidizing agent. I told you. We will be learning a lot about this oxidizing property. Then it attacks most metals except noble metals like gold and platinum. I told you. The products of oxidation depends on the concentration of the acid, the temperature, and also the nature of the material getting oxidized. Okay. So these are the important physical properties. A little bit overlapping of the chemical properties is also there, but this is what we need to know about HNO3 when we proceed on to the chemical properties. Okay. Now we have the chemical properties of HNO3. We pass on to that. As I told you, HNO3 is a strong oxidizing agent and will oxidize both metals and non-metals except noble metals. Okay, what are noble metals? They are the least reactive metals. You know, platinum, gold, then silver. These are the least reactive metals. So the noble metals, they are not very reactive. So except for them, all others will be oxidized. That is why I told you during the preparation of HNO3, in Oswald process also I told you that it is a very reactive product that we are obtaining as a result of Oswald process, that is HNO3. So only we are using a platinum gauze. I told you, platinum rhodium gauze for the preparation. As catalyst we are using that because it should not react. It is a very good strong oxidizing agent. Okay, now what we see here is that I have put an example for less reactive metal and a more reactive metal. Okay, so based on that and also on the dilution, see this is dilute HNO3 and concentrated HNO3 taken. Okay, so let us see for copper for instance. You know that copper is less reactive than zinc. Okay, so I have taken copper and zinc together. Now this is less reactive metal. Copper with plus HNO3 gives the metal nitrate, that is copper nitrate is produced, that is metal nitrate. Along with that water also is formed. That is a common product. See, metal nitrate water, metal nitrate water, metal nitrate water, metal nitrate water. So that's the common products that you should be able to write when you are asked about to write the oxidizing oxidized properties of copper with the dilute and also concentrated HNO3. Okay, so usually the question asked is which is the gas produced when copper is reacting with dilute HNO3 and concentrated HNO3. So that will be your question. Okay, or what is its reaction with the least reactive less reactive metal and a more reactive metal. So that will be the question for you. So you can see here when Cu plus HNO3 gives CuNO3 H2O and NO here. Okay, so here it will be copper and copper nitrate H2O and NO2 coming out. Okay, so in the case of concentrated the products are same. Concentrated HNO3 with the copper and also zinc, the products are same as you can see here. Okay, but in the case of zinc here, with dilute HNO3, zinc nitrate H2O and N2O is coming out. N2O is called as laughing gas. Now, laughing gas will come out if the HNO3 is dilute. So, zinc will laugh. You can think like this. Zinc will laugh if dilute HNO3 is used for oxidizing it. I hope you understood. So, zinc will be forming zinc nitrate H2O and N2O. And this will be forming NO2. Okay, zinc when it is reacting with HNO3 will be forming NO2 and NO2 will come out. I hope you understood. Now keep this in memory. Okay, it's very important reaction. Okay, now we see the oxidizing property of HNO3 with non-metals. Okay, almost all the non-metals are being oxidized by HNO3, and you can see I2 will be oxidized to HiO3, that is iodic acid, carbon to carbon dioxide, sulfur to sulfuric acid, and phosphorus to phosphoric acid. So remember these products, okay, and the rest is similar. So you can just remember the products and the other products are similar, just like in the case of metals. Okay, so I2 plus HNO3 gives HiO3 plus NO2 plus H2O. Carbon plus HNO3 gives carbon dioxide. I told you carbon dioxide plus NO2 plus H2O. These are the common products. P4 plus HNO3 gives H3PO4. This is phosphoric acid. This is sulfuric acid. So phosphoric acid plus NO2 plus H2O. And S8 plus HNO3 gives H2SO4 plus NO2 plus H2O. Okay. So here the products are all same, but you have to remember this one, what it becomes after oxidation. Okay. Now try balancing the above chemical equations too. Okay, if you can balance, you stop the video here and try to balance the chemical equation. I have balanced it here, and you can actually take down. See, this is the balanced chemical equation for the oxidation of HNO3 with non-metals. Okay, now we have come to the last portion of the the nitrates, nitrogen, which I was telling about the compounds of nitrogen and all, and now we pass on to phosphorus actually in the next slides. Now this is the last one, that is the brown ring test. It's the confirmatory test. As you know, it's a confirmatory test for NO3 nitrate. Okay, so the ability of Fe2 plus to reduce nitrates to nitric oxide. So that's what we are studying here. Okay, you know the reaction, I hope. What is done, the nitrate is taken, nitrate solution what you're given is taken in a test tube, and then and freshly prepared FeSO4 ferrous sulfate you will be taking, and along the sides inside the same test tube, and along the sides you will be pouring this H2SO4 along the sides of the test tube in a slanting position. You will hold the test tube and then you will be pouring H2SO4 along the sides of the test tube. Then we get a brown ring at the junction of the two of the two solutions. Okay, you can see a brown ring. FeSO4 will be on top, H2SO4 down under, because it is having more weight. Okay, and then you will have the brown ring in the middle here. Now what are the steps involved? NO3 minus, isn't it? Nitrate is becoming nitric oxide, NO, that you have to write. Then Fe2 plus becoming Fe3 plus. Okay, this is this is the one which is reducing, so it is getting oxidized. Fe2 plus becomes Fe3 plus, and then 4H plus to H2H2O. So this is this same reaction. I have put it like this. Now what happens is that all this combines and forms a complex like this. Okay, and then it will react with NO and gets this NO inside of this. Now listen carefully. Fe has H2O6, isn't it? So here you can see when the complex is formed, your coordination compound is formed here. Fe will be with 5 H2O. Okay, and 1 H2O will be taken out here, and NO will take its place. I hope you understood. The same compound only. This is a nitroso complex formed. Nitroso ferrous sulfate we call it, and that is what we call as a brown ring. Your teacher will be telling you about this brown ring test and how it is conducted and all. But at that time, do remember that this is how we have studied about the brown ring test and what is that brown ring that is being formed. Okay, I hope you understood. Okay, thank you. Okay. Now let's talk about the uses of HNO3, which we can't just ignore. Okay, HNO3, the uses manufacture of used in the manufacture of NH4NO3 for fertilizers, explosives, and pyrotechnics. Then that is in the manufacture of ammonium nitrate for fertilizers. Okay, and then preparation of nitroglycerin and nitrotoluene. Okay, so both these are important. So nitroglycerin, nitrotoluene, all these preparation is with the help of ammonia, and it is used for the preparation of organic nitro compounds, we usually say like that. Then it is used in the pickling of stainless steel. Pickling, I will tell you what it is. Now you just understand pickling of stainless steel. Then etching of metals. Etching, what is etching also I will tell you. And oxidizer in the rocket fuel. So these are the important uses of ammonia. Now you just see here, I have taken a picture of the the pickling process. What is pickling? So the pickling process is used to remove a thin layer of metal off of the stainless steel part, and this is used different from the descaling process, which removes visibly thick oxide scale. Okay, so the oxide scale, pickling and passivation, that's what it is. Okay, it is pacified. Both pickling and passivation are chemical treatments applied to the surface of stainless steel to remove contaminants and assist the formation of a continuous chromium oxide passive film. Pickling and passivation are both acid treatments, and neither will remove grease nor oil. So this is what is pickling. Okay, and I have actually saved a picture for you after pickling. See, pickling of stainless steel here without pickling, you can see it here. Now here with pickling, it is actually very bright and shiny, isn't it? Now another one what we have seen is etching. So this is what we call as etching. On the surface of the metals we can draw designs like this. Okay, so this is what we call as etching, and this etching is usually done with the help of acids. See, what is etching? Etching is traditionally the process of using strong acid or mordant to cut into the unprotected parts of the metal surface to create a design. Okay, and incised in the metal. Now in modern manufacturing, other chemicals may be used on other types of material, but etching was done like this. Initially you might have seen in olden pillars and all, you have seen these type of etching marks. Even in vessels, old vessels of grandma's vessels and all, you might have seen these kind of etched vessels. Okay, so it's very beautiful to see, isn't it? So this etching is also done with the help of what? With the help of nitric acid. So we just can't ignore nitric acid like that. Okay, so do learn all those uses.